it's time for us to consider another differential operator. This one is called the curl. Let's look what it is. Consider a vector field, and the curl will be an operation on that vector field, a differential operator. If you look closely at that, you will realize that this is something to do with the determinant of the vector field and of nabla operator together with the free principal unit vectors. And indeed, you can write it as the vector product between the nabla operator and the vector field. So that's again a very good use of the nabla operator. So you've seen previously that if you take a scalar product of the nabla operator with the vector field, you'll get divergence. Now you are having a vector product of the nabla operator and you have the curl. Let's look at some background. What does it actually mean? So why we need a curl? Well, let's think about a velocity field as an example of the vector field. So you have a flowing fluid and you want to characterize something about its velocity. And the curl of the velocity field is called vorticity. And it characterizes the local rotations in the fluid. What it means? It means that if you take a small ball or a cross which is fixed in the position but is able to rotate freely, then the flowing fluid might cause that rotation. And the speed of this rotation, the angular speed, will be the half of the magnitude of the curl, and the axis of rotation will be the actual curl of that vector field, of that velocity field. So that's an example why it's actually very useful to think about curls, because then you can characterize all kinds of vortices. And it's actually important how you define your coordinate system, then you talk about the curl. So if you change your coordinate system, you might change the curl. Why? Because it depends on the orientation, not just on magnitude. So if this system is right-handed, it will be the same orientation, but if you change the orientation of your coordinate system from right-handed to left-handed, then the curl will change its direction. Let's look at the example. So the example we'll consider is again an application working towards the fundamental equations of electric and magnetic fields. Let's look at the magnetic field. So let's say there's a current flowing in the z direction and it generates the magnetic field. And mu naught here is called the magnetic constant or vacuum permeability. It's just a constant. And I also assume that somebody gave us a constant value of that current. So what we're asked to do is to calculate the curl of that magnetic field. How to do it? Let's use a definition. So by definition, we write curl as the determinant of this matrix. We just expand it a bit. And notice that in the expression for a magnetic field, we didn't have the z component, and also the x and y component did not depend on z. That means that two components of the curl vector are 0. So you can see that the component which corresponds to x and y directions of the curl disappearing, they're 0. And all that we need to calculate is the z component of the curl, which is given by these two partial fractions. So let's again write down as a reminder what the components of the vector are. So again, there's no z component, and the x and y components do not depend on z. So mu naught and I are constants, pi is the mathematical constant. So let's do it by using the product and chain rules. So we take d, let's start with the y component with respect to x differentiated. So it depends on x and y, not on z. And we can write it as mu naught I over 2 pi. So we can take away the constant, take it out as a factor, with the d over dx, x squared plus y squared, and using the product and chain rules, we have mu naught I over 2 pi 1 over x squared plus y squared minus 2x times x over x squared plus y squared squared. And if we simplify it a bit, we have mu naught I over 2 pi x squared plus y squared minus 2x squared. And at the denominator, it's the same thing, right? So we cancel bit of x squared, and we finally have the derivative of the y component, which is mu naught I over 2 pi times y squared minus x squared divided by x squared plus y squared squared. So that is all we needed. So we now have that component. And we also need another component. We need the derivative of bx with respect to y. Well, we can do it, but also it's useful to notice that they're really symmetric. So the only difference is that it will be different sign here and y instead of x. So what we can do, we can just swap the order in our derivative. So if we'll want to write down what is the derivative of bx with respect to by, we replace y with x and x with y, and also make sure that we use the right sign, and we get exactly the same expression. So what you can see here is that by with respect to bx is the same as bx with respect to y, so that their difference is 0. What does it mean? It means that there is no single component of the curl which is not 0. So our entire curl is 0. So there is a no curl to that magnetic field.